Hi, welcome back. So we're in Chapter 6, Prediction by RCC, to discuss the outline prediction by classification to explore a new type of algorithm, and that is the naive Bayes algorithm. There are some assumptions it has to meet actually the algorithm requirements, which I'm going to try to highlight them as I'm exploring. But the basic concept of asking conditional probability was, what's the probability of having 1 given the input of x, for example, let's say x1. Standard form that we have discussed and actually explored a lot of example. It turns out this format of probability distribution works really well with this naive Bayes application. And the idea actually, it can be even generalized to multi-dimensional and not only on one dimension of x1 or x2. I'm going actually to explore with you maybe a simple example. If x1 and x2 happens to be a discrete kind of variable, we look at each case. So this is an input space that would have the vector of value of x1, of course, and x2. And the corresponding label to that, which is the c, is going to be, of course, a vector or a scalar. The first principle here, what we could do is to look at the data set and capture what is the probability of, for example, class 0. It's nothing special, so we're going to take the count of class 0 divided by the n, and the rest, of course, will be the probability of 1. The next thing we want to do also to create maybe cross-tabling with each of these possible outcome of x1. I have now everything is in order. Same thing, by the way, I could do to the x2. Now the next thing, what is the probability of having class 0 given the space of the x? Now the space of the x, we're talking about this guy here. If we apply this on one feature, it turns out this denominator, it can be get rid because it will be just the probability of having class 0 here multiply by the probability of x1 given of a class 0 multiplied by the probability of x2 given that class 0. So these guys here are just calculated from here. The same thing you do when you have class 1. Now what we want actually the argmax between these two values. Now this is the case when x1 and x2 discrete kind of variable. But how about the case if my actual x1 and x2 maybe are continuous? It's unlike the case here when we created this cross-table. We can't do that here. And this is where the Gaussian distribution come into play, which is the probability of a given instant that will return the probability. But there's two important assumptions. The first one, we assume that the variables are normally distributed based on Gaussian bell curve. And the second, covariance between these variables does not exist, almost close to 0. Well, in real life, this might be quite hard to achieve because dependency is in there between these two variables. But there is a small trick, maybe it can work. Let's assume that I have x1 and x2. And again, the label, binary label for now, zeros and ones, okay? And the values here are continuous. I have to create this x vector, which is going to be this instance, okay? x1 and x2. And next thing, I have to find out what is the mu of each feature. And the third one, I have to come up with the sigma. Well, the sigma is the variance of x1 and the variance of x2. And then the trick here, instead of capturing the covariance between x1 and x2, I will just put zeros here. And once that all has been done in place, then I plug that to the matrix. Then we get back to the exact same practice that we've been doing when we have a discrete value. Another word to say, well, the probability 0 given this x, which is going to be this guy, the same thing, we're going to do a probability of 1 given feature x. Now, I think from practical perspective, let's go to Python and see a practical example I have written. Now, if you remember previously in the multi-class case here, when we did this data set, if you remember, it was really hard data set and overlap. We have tried the logistic regression. Actually, the result of the prediction was quite poor. It's like 43%. That's why I have decided actually to use this naive Bayes algorithm and see what was going to happen. We were looking actually at each incidence inside this 100 test data point. So for example, for class 0, the probability like this, for class 1, the probability like this, for class 2, like this. And the maximum probability, the argmax among this one here, we know it. And we are predicting the class to be 1, which is, of course, correspond to this class. Same thing for the next and so on and so forth. So each one, the prediction is in there. Of course, I just pull out these prediction and I have to compare them with the actual labels, and that's why I did this small counter. You could see here magnificent improvement. It's 64%. If you remember in the multi-class, we used the logistic regression from sklearn, and the one we had actually built manually, it's only 43%. And keep in mind, I did not do any preparation on this data. I took it exactly as it is, and you could see how simple it was to get such a thing. 64%, it's not bad comparison to the previous one. That was all what you have to know concerning the list of these algorithms for classification. Next, I would like to take also some time discuss deep learning algorithms. That's exactly what we're going to do next. I will see you then.